representing and manipulating data in computers. Introduction. Computers are designed to receive, store, manipulate and present data. This unit explains how computers do this, with reference to the examples of a PC, kitchen scales and a digital camera. In particular, it explores the idea that the data in a computer represents something in the real world. After studying this unit you will know what all the terms highlighted in bold in the text mean. Know how the following types of data are represented in a computer, and what the limitations of such representations are. Positive and negative integers. Fractions. Analog physical quantities such as weight. True. False quantities. Still pictures. Text. Moving pictures. Sound. Know, at an introductory level, what data compression is and why it is useful. Know, at an introductory level, how input and output subsystems support the conversion of various types of information to and from data types usable by a computer. Describe what a computer program is and how it utilizes the memory in the processor. Use a flowchart to describe the implementation of a given task. Perform calculations relating to file sizes for text, still images, moving images and sound. Convert between binary and denary representations for both positive and negative integers. Perform simple arithmetic operations on pairs of 8-bit binary numbers. Find the 2's complement of a given binary number. Perform the NOT operation on 8-bit binary codes, and the AND, OR, and XOR logic operations on pairs of 8-bit binary codes, when representing data in computers. Introduction. A computer is designed to do the following things: receive data from the outside world, store that data, manipulate that data, probably creating and storing more data while doing so, present data back to the outside world. In the next few sections I am going to examine in more detail the data that a computer receives, stores, manipulates and presents. In particular, I want to explore the idea that in a computer the data represents something in the outside world. Here are a couple of examples you are probably familiar with from using your PC. The data will represent text and punctuation marks if you are using your PC to do word processing. The data will represent numbers if you are using your PC to do calculations on a spreadsheet. Many applications, not just word processors and spreadsheets, require the representation of text and/or numbers, but there are also other types of data that need to be represented. Activity 1: Exploratory. Here are 3 examples of computers: electronic kitchen scales, a digital camera and a PC. Use these examples to suggest what else will need to be represented in these computers. For instance, weights will need to be represented in the electronic kitchen scales, where they are an input. Discussion. You may have suggested the following. Numbers on a display panel outputs in the kitchen scales. Sound produced by a beeper output when the kitchen scales timer facility is used. Scenes that will be turned into still pictures inputs in the digital camera. Still pictures outputs in the digital camera and in PCs. Scenes that will be turned into moving pictures inputs in PCs with webcams. Moving pictures outputs in PCs. Music, spoken words and other types of sound inputs and outputs in PCs. Another, more subtle, input that you may have mentioned is the input from a button on the kitchen scales or digital camera. Think, for example, of the button on the digital camera that switches the flash on or off. A representation of the input from this button is an important data item in the camera's computer. It tells the computer whether flash is to be used. Data is an important part of any computer system, and sections 2 to 4 will discuss the ways in which various types of data can be represented in a computer, focusing on the 3 example computers. The kitchen scales in section 2, the digital camera in section 3 and the PC in section 4. A danger with using specific examples to introduce a general idea like data representation is that the examples may not demonstrate all the principles that need to be introduced. I have dealt with this potential problem by inserting boxes at various points in the text. These discuss ideas about data representation which are related to those in the main text but either are not relevant to the particular example under discussion, or apply more widely. You should note that the material in these boxes is accessible. The word data itself is a Latin one and its root meaning is things given, hence facts. But in the context of computers the word data has a subtly different meaning, which is a formless representation of facts, entities or ideas such that they can be manipulated, transmitted or received. Note that this means that data is therefore being given a different meaning from information. Information is also facts and ideas, but not in a formless representation for use by a computer. Information must be converted to, or expressed in, a suitable formless format, and it is this formless format which is called data. In computers all data is represented as binary codes. That is, all data is represented as strings of zeros and ones. A single binary digit, that is, a 1 or a 0, is called a bit, and that the term byte is used to refer to a group of 8 bits. Byte is the term traditionally used for a group of 8 bits in the context of computers. But octet is the term traditionally used for a group of 8 bits in the context of communications. Now that computers and communications are converging, you may meet either term in either context. You therefore need to be familiar with both terms. As with all codes, the user must know what the coding convention is in order to be able to assign meaning to it. For instance, on one occasion in a computer it may be appropriate to assign the meaning the letter J to the code 01001010. On another occasion it may be appropriate to assign the meaning the number 74 to the same code, and so on. Does this sound faintly alarming? How does the computer know whether to treat 01001010 as the letter J or the number 74 or something else? The answer is that context is crucial. If the computer has been programmed to treat the next code it receives as a letter, it will treat the code 01001010 as the letter J. If the computer has been programmed to treat the next code it receives as a number, then it will treat the code 01001010 as the number 74. And if it has been programmed to treat the next code it receives as something else, then it will treat the code 01001010 as it's something else. Inside a computer, the codes are grouped into predefined numbers of bits. Sometimes, particularly in relatively simple computers such as the kitchen scales, these predefined groups are bytes. But many computers are designed to handle a longer group of bits as a single entity. Modern PCs handle 32-bit groups, and it is likely that they will be handling 64-bit groups in the near future. A fixed-length group of bits that is handled in a computer as a single entity is called a data word, or simply a word, and the number of bits in the word is referred to as the word length. Thus most PCs work with a word length of 32 bits. 2. Representing data in the kitchen scales. 2. 1. Introduction. Study note. You may like to click on the link below to the numeracy resource as you study section 2. It offers additional explanations and extra practice on some of the topics, and you may find this useful. Click on the View Document link below to open the numeracy resource. View Document. Figure 9. 3 photos of the kitchen scales display. With the scales weighing in imperial units. Figure 9. 3 photos of the kitchen scales display. With the timer function in operation. Figure 9. 3 photos of the kitchen scales display. Negative values can be displayed for weights if the add and weigh facility is being used. The kitchen scales above provide examples of several different types of data that need to be represented. I'll start with an output. The display panel on the front of the scales. This can display numbers. Integer whole numbers of grams. Numbers of ounces including fractions. Even negative numbers when the add and weigh facility is in use. In sections 2 to 4 I shall discuss how integer numbers which are positive, fractions and negative numbers respectively can be represented inside the computer. As far as the inputs to the computer are concerned, the most important one is the weight in the scalepan. You may think that representing a weight inside a computer is simply a matter of representing a number, and to some extent you would be right. But there is a complication, which I'll explain in section 2. 5. Next I'll deal with the input that controls whether the scales are to weigh in metric or imperial units, and the output that controls whether the beeper that's used in the timer function is on or off. Representing both of these needs a true false quantity, as I'll explain in section 2. 6. All of the above deal with the codes that are used to represent the data. I'll conclude section 2 with a brief look section 2. 7 at the ways in which input and output are handled so that the computer can obtain the data it uses, and subsequently present the user with appropriate data. 2. Representing numbers. Positive integers. A very straightforward way of finding binary codes to represent positive integers is simply to use the binary number that corresponds to each integer. This is because every positive integer in the everyday number system known as the decimal or denary system, because it uses 10 different digits, has a corresponding number in the binary number system. As you will see later, in section 7 of this unit, just as arithmetic, addition, subtraction, etc. can be performed on everyday denary numbers, so it can also be performed on binary numbers. This means that encoding denary numbers as binary numbers is particularly useful whenever an application will include an arithmetic. And this is the case with the kitchen scales, thanks to their add and weigh function. You need to know something about binary numbers, and so in this section I shall first remind you of an important principle of the number system you are already familiar with, the 10-digit decimal or denary system, then show how that principle applies to the 2-digit binary number system. I'll also show you how to convert between the two systems. 1 Positive integers. Denary numbers. The number system which we all use in everyday life is called the denary representation, or sometimes the decimal representation, of numbers. In this system, the 10 digits 0 to 9 are used, either singly or in ordered groups. The important point for you to grasp is that when the digits are used in ordered groups, each digit is understood to have a weighting. For example, consider the denary number 549. Here 5 has the weighting of hundreds, 4 has the weighting of tens, and 9 has the weighting of units. Try saying 549 aloud. 549. If you remember that I is a corruption of 10, you can see that the way the number is said is exactly consistent with this idea of weightings. So 549 stands for 5 102 plus 4 101 plus 9 100, which is 5 100 plus 4 10 plus 9 1. In the foregoing, the raised numbers after the various tens are called exponents. If you are unfamiliar with exponent notation, you should note that 102 means 10x 10, 103 means 10x 10x 10, and so on. 101 simply means 10, and 10 is taken to be 1. There is more about this in the numeracy resource. Click on the link below if it's an unfamiliar idea to you. Please click on the View Document link below to view the numeracy resource. View Document. The position of the digit in the group is therefore crucial in determining its weighting. The leftmost digit in the group 5 in the above example is called the most significant digit because it is the most heavily weighted digit. Similarly, the rightmost digit 9 above is called the least significant digit. A number representation like this, where a digit's position determines its weighting, is called a positional notation. Notice the pattern of the exponents. They increase by 1 from right to left. Activity 2 Self-assessment. In the denary number 10276, what are the weightings of the 7, the 0, the 1? What is the most significant digit? Write out this number in a similar way to the way 549 was written out on the preceding text, that is, as a sum of terms of the form digit 10 to some exponent. Answer 1. Tens. The 7 represents 70 thousands. There are no thousands. 10 thousands. The 1 represents 10. 104 plus 0 103 plus 2 102 plus 7 101 plus 6 100. 2 positive integers. Binary numbers. Just as a denary number system uses 10 different digits 0, 1, 2, 3, 9, a binary number system uses 2 0, 1. Once again, the idea of positional notation is important. You have just seen that the weightings which apply to the digits in a denary number are the exponents of 10. With binary numbers, where only 2 digits are used, the weightings applied to the digits are exponents of 2. The rightmost bit is given the weighting of 2, which is 1. The next bit to the left is given a weighting of 21, which is 2, and so on. Thus the 4-bit binary number 1101 represents. The leftmost bit is called the most significant bit M. S, B, and the rightmost bit is called the least significant bit L, S, B. Computers are designed to work with binary numbers, but denary numbers suit most people better. Humans therefore need to interpret the 4-bit binary number 1101 as follows: 123 plus 122 plus 021 plus 120, which is 8 plus 4 plus 0 plus 1 equal 13 inches denary. Activity 3, self-assessment. What does the 4-bit binary number 1010 represent? To what denary number is it equal? What is its most significant bit? Answer: 1010 represents. It is equal to 8 plus 0 plus 2 plus 0 equal 10 inches denary, and its most significant bit is 1. Exactly the same principles can be applied to larger binary numbers. For example, in an 8-bit word, the most significant bit has a weighting of 27, which is 128. So 10,110,110 represents and equals 128 plus 0 plus 32 plus 16 plus 0 plus 4 plus 2 plus 0, which is 182 inches denary. It is often convenient to number the bits in a binary word and to refer to the bits as bit 5 or bit 2. And the most convenient way of numbering the bits is to use the exponents in the weightings. So the bits are usually numbered as follows for an 8-bit word: 7654321, bit number 27, 26, 25, 24, 23, 22, 21, 20 weighting. This scheme means that the least significant bit is bit 0 and the most significant bit is bit 7, just as a space between groups of 3 digits in large numbers e. g. 625, 127 can make them easier to read, so spaces between groups of 4 bits can make binary numbers easier to read. I shall use spaces in this way. So I shall write, for example, 10011110 rather than 10,011,110. Note that the space is purely for convenience in reading the number. It does not affect the value of the number in any way, nor the way the computer handles it. Activity 4, self-assessment. To what denary number is the binary number 1100-0110 equal? In a 16-bit word, what is the weighting of the most significant bit? What bit number should be allocated to this bit? To what denary number is the binary number 1000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000 equal? Note that Windows has a calculator in accessories that will evaluate numbers like 210, 214, etc. You will need to choose scientific from its view menu and then use the XY key. For instance, to find 210, press 2 then XY then 10 then equal. You should get 1024. Answer: omitting the zeros because they do not contribute to the sum. This binary number is equal to 127 plus 126 plus 122 plus 121, which is 128 plus 64 plus 4 plus 2 equal 198 inches denary. In an 8-bit word, the weighting of the most significant bit is 27. By noting that 7 is 1 less than 8, you can see that the weighting of the most significant bit in a 16-bit word will be 215. 215 is equal to 32,768 and the bit number is 15. It is the same as the exponent of 2. It is equal to 215 plus 120, which is 32,768 plus 1 equal 32,769 inches denary. Counting in binary is very simple because there are only 2 possible digits. It proceeds as follows: 0, 1, 10, 11, 100, 101, 110, 111, 1000, etc. Notice that when all the bits in any number are 1, the next higher number needs 1 more bit to represent it. This is exactly analogous to denary, where 999 is followed by 1000, which needs 1 more digit to represent it. Activity 5, self-assessment. A what binary number follows? B. What binary number precedes 1000,000? Answer: AI 10,000. E 1000. B 111 11 11 or 0111 11 11 if an 8-bit word is to be used. 2. 3 positive integers. Converting denary numbers to binary. If computers encode the denary numbers of the everyday world as binary numbers, then clearly there needs to be conversion from denary to binary and vice versa. You have just seen how to convert binary numbers to denary, because I did a couple of examples to show you how binary numbers work. But how can denary numbers be converted to binary? I'll show you by means of an example. Example 1. Convert 219 to an 8-bit binary number. Answer. First write out the weightings of an 8-bit number. 27, 26, 25, 24, 23, 22, 21, 2128, 64, 32, 16, 8, 4, 2, 1. Now decide whether the given number, 219, is larger than or equal to the largest weighting, 128. If the given number is larger than or equal to the weighting, record a 1 in the 128 column and subtract the weighting from the number. But if the given number is smaller than the weighting, record a 0 in the 128 column. Here 219 is bigger than 128. Hence a 1 goes into the 128 column. There is 128 in 219. This is shown below. The result of the subtraction 219? 128 is 91. 27, 26, 25, 24, 23, 22, 21, 2128, 64, 32, 16, 8, 4, 2, 1, 1. Now decide whether the result of the subtraction, 91, is larger than or equal to the next lower weighting, 64. I'll just call the result of the subtraction a new number. If the new number is larger than or equal to the weighting, record a 1 in the 64 column and subtract the weighting from the new number. If the new number is smaller than the weighting, record a 0 in the 64 column. Here 91 is larger than 64, hence a 1 goes into the 64 column. There is 164 in 91. This is shown below. The result of the subtraction 91? 64 is 27. 27, 26, 25, 24, 23, 22, 21, 2128, 64, 32, 16, 8, 4, 2, 1, 1, 1. Now decide whether the new number, 27, is larger than or equal to the next lower weighting, 32. If the new number is larger than or equal to the weighting, record a 1 in the 32 column and subtract the weighting from the new number. If the new number is smaller than the weighting, record a 0 in the 32 column. Here 27 is smaller than 32. Hence a 0 goes into the 32 column. There are number 32s in 27. 27, 26, 25, 24, 23, 22, 21, 2128, 64, 32, 16, 8, 4, 2, 1, 1, 1, 0. Now decide whether the number brought forward, 27, is larger than or equal to the next lower weighting, 16. If the number brought forward is larger than or equal to the weighting, record a 1 in the 16 column and subtract the weighting from the new number. If the number brought forward is smaller than the weighting, record a 0 in the 16 column. Here 27 is larger than 16. Hence a 1 goes into the 16 column. There is 116 in 27. This is shown below. The result of the subtraction 27? 16 is 11. 27, 26, 25, 24, 23, 22, 21, 2128, 64, 32, 16, 8, 4, 2, 1, 1, 1, 0, 1. The process continues for the last 4 remaining weightings, and you can check for yourself that the final result is 27, 26, 25, 24, 23, 22, 21, 2128, 64, 32, 16, 8, 4, 2, 1, 1, 1, 0, 1, 1, 0, 1, 1. The binary number can now be read off. It is 11011011. Sometimes the first bit, or the first few bits, turn out to be 0, as would be the case if, say, denary 6 was being converted to an 8-bit number. These leading zeros must be included in the resulting binary number, otherwise it would not be 8 bits long. So, for example, 6 is 0000110 in 8-bit representation. The same principles as those illustrated in the example above apply to other word lengths. The important point is to start the comparison and subtraction process with the weighting of the most significant bit for the word length you are using. Activity 6 Self-Assessment. A convert denary 7 into a 4-bit number. B. Convert the following denary numbers into 8-bit numbers. Answer. Here the weightings are 8, so a 0 goes into the 8 column. Going on to the next lower weighting, 4. 7 is larger than 4, so a 1 goes into the 4 column. The subtraction is 7, 4, which is 3. Continuing like this gives, so the binary number is 0111. Be here the weightings are those given in example 1. I120 is smaller than 128, so 0 goes into the 128 column. 120 is larger than 64, so a 1 goes into the 64 column. The subtraction 120? 64 gives 56. 56 is larger than 32, so a 1 goes into the 32 column. The subtraction 56? 32 gives 24. And so on. The result is, so the binary number is 01111,000. Similarly, appropriate comparisons and subtractions here give, so the binary number is 00001101. Activity 7 Exploratory. Is there more than one possible result of converting a denary number into a binary number? Look back at the conversion of 219 my example and of 7, 120 and 13 activity 6 to help you to decide. Discussion. There is only one possible pattern of 1s and 0s in binary that equals a given denary number. You can alter things slightly by saying whether you want a 4-bit, 8-bit, 16-bit, etc. word. For example, denary 7 is 0111 in a 4-bit word, but 0000111 in an 8-bit word, but the essence of the pattern stays the same. This is because there is only one possible outcome of the comparison at each stage of the conversion process. Either the number you are working with is larger than or equal to the next weighting, or it is smaller than the next weighting. There is no possible ambiguity. Hence the pattern of 1s and 0s is fully defined and only one appropriate pattern can exist. In conclusion, then, if the denary number to be encoded is a positive integer, a positive whole number, then the number is converted to binary form, as just described, so that it can be stored or manipulated in the computer. And after manipulation the result can be converted back to denary for reporting the outcome to the user. In the kitchen scales, for example, the weight is displayed as a denary number on the display. Box 1. Distinguishing between binary and denary numbers. Very often it's obvious whether a given number is binary or denary. 2975 is denary, and 00111010 is very likely, though not absolutely certain, to be binary. But is the number 1001 binary or denary? One way of distinguishing clearly between binary and denary numbers is to write a subscript 2 at the end of a binary number and a subscript 10 at the end of a denary number. Thus 10,012 is binary because of the subscript 2 at the end, whereas 100,110 is denary because of the subscript 10 at the end. Sometimes binary numbers are described as being to base 2. This fits with a subscript 2 at the end of the number. Similarly, denary numbers can be described as being to base 10, and this fits with a subscript 10 at the end. You will meet the subscript convention on occasions in the rest of the unit. 2. 4 positive integers. Encoding larger integers. The examples and activities in this section have looked only at 8-bit numbers. They have illustrated all of the principles of encoding positive integers as binary numbers without introducing the complication of larger numbers. But of course with 8 bits only relatively small integers can be encoded. Activity 8 Self-assessment. What is the largest positive integer that can be encoded using just 8 bits? Answer. The largest 8-bit binary number is 11111111. This is 128 plus 164 plus 132 plus 116 plus 18 plus 14 plus 12 plus 11, which is 255. So this is the largest positive integer that can be encoded. There is a pattern to how many different integers can be encoded by a given number of bits. You have just seen in activity 8 that with 8 bits 1 byte only the denary integer 0 to 255 can be encoded. This is 256 different integers in all. So 8 bits can encode 256 different integers, and 256 is 28. If you check, you will find that with 4 bits 16 different integers can be encoded, with 6 bits, 64 different integers. This leads to the general rule that with n bits 2n different integers can be encoded. Using this general rule, 16 bits can encode 216 different positive integers, which is 65,536. So the denary integer 0 to 65,535 can be encoded in 16 bits, which is 2 bytes. Similarly, 32 bits can encode 232 different positive integers, which is 296. So the denary integer 0 to 295 can be represented in 32 bits, which is 4 bytes. Activity 9 Exploratory. Did you notice that I said that with 2 bytes 65,536 different positive integers can be encoded, and then that they are 0 to 65,535? Why did I not say that they are 0 to 65,536? Discussion. In this method of encoding, a code of all zeros always represents denary 0. This leaves only 65,536. 1 equals 65,535 other patterns of zeros and ones to represent other integers. So only the 65,535 integers 1 to 65,535 can be represented along with the 0. The kitchen scales have been designed so that when they are weighing in metric they can weigh up to 3,000 grams, in whole numbers of grams. I'm going to ignore for the moment the fact that the kitchen scales can handle both positive and negative integers, which is an added complication that I shall come to in section 2. 4. Imagine that the scales did not have the added weigh facility and so did not need to deal with negative numbers. Then they would simply need to be able to encode positive integers from 0 to 3,000. Activity 10 Exploratory. How many bits are needed to encode positive integers from 0 to 3,000? Hint. You already know that 8 bits would offer too few codes. 28 equal 256 and 16 too many. 2 equals 65,536. So try some numbers between 8 and 16. Discussion. 11 bits would offer 48 different codes, which is too few. 12 bits offered 4096, which is more than enough. So 12 bits are needed to encode positive integers from 0 to 3,000. Now it so happens that the computer in the kitchen scales uses 8-bit words. So how could it cope with the fact that 12 bits are needed to hold the codes for the weights in grams? The answer is very simple. 2 words would be used. One word would hold the rightmost 8 bits of the code, the other word the leftmost 4 with some spare bits that are not used. Figure 2 illustrates this for the code 0101011100. Note that the word on the left in figure 2 is the most significant, as it holds the most significant bits of the code word. The one on the right is the least significant. Figure 2. The 12-bit code word 0101011100 is held in 2 8-bit data words. Provided the program had been carefully designed to take account of this arrangement, everything would work just fine. A representation that uses more than one word is known as a multiple-length representation. Activity 11 Self-assessment. Read box 2 binary coded decimal to help you to answer this question. What is the denary equivalent of the binary word 01010110 if it represents a natural binary number? A binary coded decimal number with 2 code words packed into the single 8-bit word. Answer. 1. The 8-bit number is equivalent to 0128 plus 164 plus 032 plus 116 plus 08 plus 14 plus 12 plus 01, which is 86 inches denary. 2. The 8-bit number is now equivalent to denary 5 then denary 6, which is denary 56. Box 2. Binary coded decimal. The coding system described in section 2. 2 is known as the natural binary coding system. It uses the binary counting number 0, 1, 10, 11, 100, etc. to encode the denary counting number 0, 1, 2, 3, 4, etc. There is an alternative coding system which is sometimes used. It is known as binary coded decimal or BCD. Here each digit of a denary number is coded by its 4-bit binary equivalent. This results in as many 4-bit code words as there are digits in the original denary number. So for example, denary 25 is encoded as 00102, then 01015, and denary 139 as 00011, then 00113, then 1019. In a computer with, say, a 16-bit word length, 4 BCD code words can be packed into a single computer word if desired. Alternatively, each code word can form the least significant 4 bits of a 16-bit word, with the other bits set to 0. It is important to make a decision on this point in each individual application, and then adhere to it. 2. 3 representing numbers. Fractions. In the denary system, a decimal point can be used to represent fractions, as in 6, 5 or 24, 29. One way of encoding fractions uses an exactly analogous method in binary numbers. A binary point is inserted. Some examples of 8-bit binary fractions are 0, 0010110, 01101010110, 1. The weightings that are applied to the bits after the binary point are, reading from left to right, 1, 2, 1, 4, 1, 8, etc. In just the same way as in denary fractions they are 1, 10, 1, 100, etc. Now, 1, 4 is the same as 1, 22, and 1, 8 is the same as 1, 23, and there is a convenient notation for fractions like this, which is to write 1, 22 as 2, 2, 1, 23 as 23, and so on. In other words, a negative sign in the exponent indicates a fraction. Using this notation, the bits after the binary point in a binary fraction are weighted as follows: 2, 1, 2, 2, 2, 3, 2, 4, 1, 2 equals 0, 5, 1, 4 equals 0, 25, 1, 8 equals 0, 125, 1. 16 equals 0.0625. So, for instance, 0.0101,000 inches binary is equal to 1. 4 plus 1. 16 equal 5. 16 or 0. 25 plus 0.0625 equals 0.3125 inches denary. One problem with encoding fractions like this is that there is no obvious way of representing the binary point itself within a computer word. Given the 8-bit number 01011,001, where should the point lie? The way of solving this problem is to adopt a convention that, throughout a particular application, the binary point will be taken to lie between two specified bits. This is called the fixed point representation. Once a convention has been adopted, for example, that the binary point lies between bits 7 and 6, it should be adhered to throughout the application. Another problem is that it may not be possible to represent a denary fraction exactly with a word of given length. For example, it is not possible to represent denary 0, 1 exactly with an 8-bit word. The nearest to it is binary 0, 0001101 with a denary difference of 0, 0015625. Try it for yourself. So it is just not possible to represent all fractions exactly with a binary word of fixed length. This second problem can be reduced, but not eliminated, if a multiple length representation is used. For example, with 12 bits the denary fraction still cannot be represented exactly, but now the nearest to it is binary 0, 0001101 with a much smaller denary difference of 0.00009765625. Fortunately, this problem of exact representation does not occur in the kitchen scales example. In recipes using imperial weights, it is traditional to use 1, 2 ounces, 1, 4 ounces, etc., and these are fractions which can be exactly represented by the fixed point representation just described. Box 3. Floating point representation. Another way of representing binary fractions is by the floating point representation. This is the preferred method in many applications as it is a very flexible method, though rather complex. It uses the same basic idea as a fixed point fraction, but with a variable scale factor. Two groups of bits are used to represent a single quantity. The first group, called the mantissa, contains the value of a fixed point binary fraction with a binary point in some predefined position, say, after the most significant bit. The second group, called the exponent, contains an integer that is the scale factor. An example is a mantissa of 0, 111 1000, which evaluates to the fixed point fraction 1, 2 plus 1, 4 plus 1, 8 plus 1, 16 equal 15. 16, together with an exponent of 0.000011, which evaluates to the denary integer 3. But what fraction does this mantissa exponent pair represent? The answer is that it represents mantissa to exponent, which is 15. 1623. This works out to 15. 16.8, which is 7. 5. Another example is a mantissa of 0. 0.110000 and an exponent of 0.000001. Here the mantissa evaluates to 1. 2 plus 1. 8, which is 3. 8. The exponent evaluates to 1. So the fraction represented here is 3. 821. This works out to 3. 82, which is 3. 4. Notice that the fraction being represented in the first example is a mixed fraction, that is, a mixture of an integer and a fraction which is less than 1, while in the second example the fraction being represented is simply less than 1. This ability to represent both types of fractions with identical encoding methods makes the floating point representation extremely versatile. 2. For representing numbers. Negative integers. In section 2, I showed you how integers can be encoded if they are known to be positive, treating the integers in the kitchen scales as if they were known to be positive. However, if the user invokes the add and weigh function on the scales while there is an object in the scale pan and then removes the object, the display should record a negative value. Hence the computer in the scales must be able to carry out subtractions and deal with resulting negative values. If the user is moving several things on and off the scale pan, invoking the add and weigh function on occasions, then the computer must be able to determine at all times what value it is to display and whether this value is positive or negative. The computer must, therefore, be able to do arithmetic, B to handle negative values, and C to distinguish between positive and negative values. In this section I shall show you how negative numbers can be encoded and distinguished from positive numbers. The aspect of arithmetic will be dealt with later, in section 7. An integer which may be positive or negative is known as a signed integer. In any code system for signed integers, it is important to indicate whether the integer is positive or negative. With ordinary denary numbers, a signed positive integer is prefixed by a plus sign and a signed negative integer is prefixed by a minus sign. Each signed integer has an additive inverse which is obtained by replacing the plus sign by a minus sign, or vice versa. For example, plus 5 has the additive inverse 5. 20 has the additive inverse plus 20, and so on. A number and its additive inverse have the property that 0 is obtained when they are added together. The system of representation is called the sign and magnitude system. You will probably be very familiar with the sign and magnitude system, and it is tempting to try to find a way of using it for binary numbers, perhaps by making the most significant bit into a signed bit and saying that 0.00000101 is plus 5 while 100101 is 5. Unfortunately, however, this coding system would make arithmetic with binary numbers awkward for computers, and so it is not normally used. The coding system that is used adapts the positional notation I introduced in section 2 to allow for negative numbers. Specifically, the most significant bit is given a negative weighting. With 8-bit codes, the weightings are then as follows. The advantage of the system is that it makes the addition and subtraction of signed integers more straightforward for the computer's processor, as you'll see in section 7. Example 2. Convert the signed binary integer 11010110 to denary. Answer. Using the weightings for 8-bit signed integers, 11010110 is equivalent to 27, 26, 25, 24, 23, 22, 21, 20. 128 64 32 16 8 4 2 1 1 1 0 1 0 1 1 0, which is 128 plus 64 plus 16 plus 4 plus 2 equal 42 inches denary. In this coding system, the leftmost bit 7 is 0 for a positive number and 1 for a negative number, so at first glance you might think of it simply as a sign bit. But this leftmost bit does more than simply acting as a sign bit. It contributes 128 to the number whenever its value is 1, thereby forcing the number to be negative whenever it is 1. The system of encoding is called the 2's complement system, and the resulting codes are often referred to as 2's complement numbers. The process of converting a positive denary 8-bit number to its 2's complement equivalent is almost identical to the process of converting a denary number to an ordinary binary number. As it is positive, it cannot have a minus 128 inches and so the leftmost bit is 0. The conversion process then starts by comparing the largest positive power of 2 with the given number. If a negative denary number is to be converted, however, it must first be expressed as a sum of a negative and a positive number, as the following example shows. Example 3. Convert the denary number 122 to an 8-bit 2's complement number. Answer. The sign bit of an 8-bit 2's complement number has weighting 128. Therefore, 122 must be expressed as 128 plus a positive number. Clearly here the appropriate positive number is 6, so 122 is 128 plus 6. Because the number contains 128, the leftmost bit of the binary representation is 1. The other 7 bits are the 7-bit binary equivalent of 6, which is 000110. So the 8-bit 2's complement equivalent of 122 is 100110. The rule is first to add 128 to the negative number, then to convert the result to a 7-bit binary number. The 8-bit number is formed by prefixing the 7-bit number by 1 because there is 128 in the given negative number. Note that 1 inch denary is 128 plus 127 and so is equal to 11 inches 2's complement representation. Activity 12 Self-assessment. What denary number is equivalent to each of the following 2's complement numbers? 10, 11, 01, 11, 01, 01, 10, 11. What is the 8-bit 2's complement equivalent of the denary numbers? 25, 96, 2. Answer. AI the number is equivalent to, which is 128 plus 32 plus 16 plus 4 plus 2 plus 1 equal 73 inches denary. E the number is equivalent to, which is 64 plus 16 plus 8 plus 2 plus 1 equal 91 inches denary. BI 25 is positive, so the leftmost bit is 0. The remaining 7 bits are used to represent 25, which is 0011,001 inches 7-bit binary. The 8-bit 2's complement number is therefore 00011001. E. 96 must be expressed as 128 plus a positive number. That is, as 128 plus 32. The leftmost bit is 1 representing the 128 and the remaining 7 bits are equivalent to 32, which is 01000000. The 8-bit 2's complement number is therefore 10100000. E. 2 is 128 plus 126. The leftmost bit is 1 representing he. 128 and the remaining 7 bits are the 7-bit binary equivalent of 126, which is 1111110. The 8-bit 2's complement number is therefore 11111110. In the 2's complement system, if an 8-bit word is used, the largest positive number that can be represented is 01111111, which is plus 127, and the largest negative number that can be represented is 1000, which is 128. In total, 127 positive numbers, 0 and 128 negative numbers, that is, 256 different numbers can be represented, which is to be expected from 8 bits. If more than 8 bits are used, then a greater range of numbers can be represented. For instance, a 16-bit word can represent signed integers in the range 32,768 to plus 32,767. In the case of a 16-bit number, the leftmost bit, in this case bit 15, again acts as a signed bit. The weighting of this bit is 215, and the weightings of the remaining 15 bits are 214, 213, 20. Activity 13, Exploratory. You saw in section 2 that 12 bits would be needed to encode the positive values 0 to 3000 if the kitchen scales worked with only positive integer numbers of grams. But of course they work with both positive and negative integers, and so the computer must be able to cope with this. What is the smallest number of bits that is needed to encode the signed integers? 3000 to plus 3000? Discussion. Did you spot that the number of bits is simply 1 more than the 12 needed for positive integers, because twice as many values now need to be represented? So 13 bits would be sufficient. In practice, of course, the computer will simply use two 8-bit words. 2. 5 representing weight. A physical quantity such as weight is the property that it can take on any value, not just a finite set of values. For instance, at one time the ingredients in the scalepan could weigh 2,569,427 grams, at another time 125. 1,234,659 grams, at yet another 2805. 87,625,922 grams. It may not be possible for the scales to display such values, but they are physically possible. Quantities like weight whose values can take on any value in this way are said to be analog. Figure 3 may help to make this clearer for you, as it is a diagrammatic representation of an analog quantity. At the top it shows a number line with gradations from 1 to 10. You can think of this as an analog quantity that can vary in value between 0 and 10. Numbers between, say, 5 and 6, such as 5, 1 or 5, 9 exist on the number line at the top of figure 3, though they have not been explicitly picked out. You can see they exist if you look at the magnified number line between 5 and 6, where the gradations explicitly show 5, 1, 5, 2, etc. But numbers between, say, 5 and 5, 6 also exist on this line, though they have not been explicitly picked out, as you can see on the even more magnified number line at the bottom of figure 3. And this process could go on indefinitely, using greater and greater magnifications to see finer and finer distinctions. There are no breaks or gaps in the line that will be revealed by some increased magnification. And this is exactly what is true of an analog quantity. There are no breaks or gaps in the values it can take. Figure 3, a diagrammatic representation of an analog quantity. Figure 3 also serves to show the problem that arises when an analog quantity is to be represented digitally, because the digital representation is rather like the markers along the lines of figure 3. It can only take one of a set of finite values. If in a particular digital representation only the values 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, up to 10, 0 are possible, then an analog value such as 5, 53, see the bottom line in figure 3, which lies between 5 and 5, 6, will have to be represented digitally by either 5 or 5, 6. In practice, 5 would be used as it is closer. Returning to the example of the kitchen scales, the fact that weight is an analog quantity presents the difficulty I have just discussed when it is to be represented digitally. Its value cannot be represented exactly. So a design decision has to be taken as to how exact the weight's representation is to be to the nearest 10 grams, to the nearest gram, to the nearest 0, 1 grams, and a number of bits has to be allocated accordingly. As you have already seen, in metric mode the scales weigh to the nearest gram. Hence they represent 29. 2,569,427 grams as 29 grams, 125. 1,234,659 as 125 grams and 2805. 87,625,922 grams as 2806 grams. The infinitely large number of possible values between 0 and 3,000 grams has been cut down to just 3,001 values, the integer numbers of grams between 0 and 3,000 inclusive. The process of segmenting an analog quantity such as weight into a finite number of values is known as quantization, and the gap between consecutive values is known as the quantization interval. In the case of the scales, the quantization interval is 1 gram. The difference between the exact weight to be represented and the nearest of the finite number of values which can represent it is known as the quantization error. In the above example of the scales, the largest possible quantization error is 0.5 grams because no actual weight value is more than half a gram from an integer number of grams. Figure 4 illustrates the idea of quantization. The red lines represent the digital values that the scales work with. They are integer numbers of grams, and you can see that the quantization interval is 1 gram. Any value from 29.5 grams up to just under 30.5 grams will be quantized to 30 grams, so the maximum quantization error is 0.5 grams. Figure 4. The quantization interval is 1 gram and the largest possible quantization error is 0.5 grams. Box 4. Reducing the quantization error. The quantization error can be made smaller by using a larger number of bits to represent values of the analog quantity. You already know that, because the kitchen scales are to weigh up to 3,000 grams to the nearest gram. 3,001 different positive weight values are to be represented in the computer and 12 bits are needed to represent each possible value. But suppose the manufacturers had decided to represent weights to the nearest 0.1 gram instead of the nearest gram. Then there would be around 10 times as many possible positive weight values to represent. 30,001, to be exact. Now, 15 bits are needed to hold 30,001 different values. That's 3 extra bits per value. So the quantization error has been reduced by reducing the quantization interval. This means that the weight is being represented more closely, but at the expense of using more bits to hold the binary code. Whether this is worthwhile in any particular situation will depend on why the values are being recorded and what they will be used for. In the case of domestic kitchen scales, it is unlikely that recipes will call for less than whole numbers of grams, but in a delicate laboratory experiment it may be necessary to measure and record values not just to the nearest 0.1 gram but to the nearest 0.001 gram. A further complication with representing weights arises from the fact that the weight in the scale pan may be changing. Some of the changes are sudden and isolated, for example when the user places a slab of butter into the scales to weigh it. Other changes may be ongoing, for example when the user slowly adds flour to the scale pan until a required weight has been achieved. Clearly it is necessary to take measurements sufficiently often and to represent each measurement separately. Measurements taken at intervals are called samples. In order to decide how often samples need to be taken, another design decision, it is necessary to know how rapidly the weight is likely to be varying and also what the user will feel comfortable with. For the kitchen scales, probably every 1/10 of a second or so would be an appropriate rate at which to sample. In some industrial situations it may be necessary to sample much more frequently, or it may be adequate to sample much less frequently. Although I have focused on representing weights in this section, what I have said is also applicable to a whole range of other physical quantities. For example, temperature, length, pressure, etc. Bear this in mind as you try Activity 14. Activity 14 Self-Assessment. A particular computer is designed to record the temperature of an oven in an industrial process to the nearest 0.1 C. The temperature can vary from 200 C to 250 C. What is the quantization interval? How many different finite values could a temperature sample take, and how many bits are needed to represent this number of finite values? What is the largest possible quantization error? Answer. The quantization interval is 0. 1 C. The temperature values in C could be 200, 0, 200, 1, 200, 2, etc., up to 250, 0. This is 501 possible values. 8 bits can only hold 256 different values, so 8 bits are not enough. But 9 bits can hold 256 equal 512 bits, so 9 bits would be sufficient. The maximum possible quantization error will occur when the actual temperature is exactly halfway between two possible values, e.g. 200, 05 C, so it is 0, 05 C, 2, 6 representing true, false quantities. Sometimes a quantity that is to be represented in a computer has only two possible values, either true or false. An example of such a true-false quantity in the kitchen scales is the one that represents whether the scales are to weigh in metric or in imperial measure. The value of this true-false quantity is given by the true-false response to the statement. The most recent push of the input button made the measuring system metric. Activity 15 Exploratory. The beeper on the timer facility on the scales is either on sounding or off silent. The value of a true-false quantity can be used to represent whether it is on or off. What do you think the statement is that will generate true-false responses for the state of the beeper? Discussion. It could be the beeper is on. Then, if the response is true, the true-false quantity will be true and the beeper will be sounding. If it is false, the true-false quantity will be false and the beeper will be silent. Note that an alternative is that the statement is the beeper is off. It is up to the designers to decide which statement is more appropriate in the system and then design the rest of the system to correspond. True-false quantities such as these are very readily represented by a single bit. All that's needed is to decide whether one represents true or false. Some computers use a single word to hold the value of a true-false quantity, in which case a decision has to be made as to which of the bits in the word is the one that will change depending on whether the value is true or false. An 8-bit word can, however, hold the values of 8 separate true-false quantities if required, making a very compact data representation. This idea could be used for the 7-segment displays in the kitchen scales. Suppose that each individual segment is numbered as shown in Figure 5a. Note that most 7-segment displays, including the one used in the kitchen scales, have a decimal point, so I have included one in the figure, Figure 5. Numbering the segments of a 7-segment display. B. The 7-segment display showing the digit 3. The state of each segment can be represented by the true-false quantity implied by the truthfulness of the statement the segment is lit. If 1 represents true and 0 represents false, then the state of the 8 segments when displaying the digit 3 see Figure 5b would be segment 0 equals 0, segment 1 equal 1, segment 2 equal 1, segment 3 equals 0, segment 4 equal 1, segment 5 equal 1, segment 6 equals 0, segment 7 equal 1. The segments represented by bits 1, 2, 4, 5 and 7 are on. The others are off. This is encoded in very compactly one word as 76543210, segment 76543210, bit number 101101110. A true-false quantity like the ones I have been describing in this section is sometimes called a Boolean variable. Hence a Boolean variable is one whose value will be either true or false. Activity 16 Self-assessment. At one time the 7-segment display is showing the digit 2. How would this be represented using the same convention as in the text above? Answer. Using the same convention, the 8-bit word would be 10, 11, 10, 10 because segments 7, 5, 4, 3 and 1 would be lit. 2. 7 input and output considerations. So far in section 2 I have focused on how the data is represented, or encoded, inside the weighing scales computer. But how does it get into the computer? And how does it get out again in a form that users can recognize? These are big questions, and ones that later parts of the course will be going into in some detail. But I can sketch some answers here. Weight is the most important input in the kitchen scales. To detect a weight, sensors are placed under the scale pan. They produce an electrical output whose magnitude depends on the magnitude of the weight in the scale pan. This electrical output is fed to the input subsystem. One of the tasks of the input subsystem is to sample the electrical output of the sensors and convert the value it finds to another electrical signal, one that is digital and therefore quantized. The other task of the input subsystem is to encode this digital signal as a binary number which represents the weight. A device that converts an analog input to a digital output is called an analog to digital converter or simply an AD converter, and the conversion process is called analog to digital conversion or simply AD conversion. The input subsystem must therefore include an analog to digital converter. Other inputs to the scales come in the form of button presses. Button presses simply close an electrical contact, a switch, and so cause an electrical current to flow. The associated input subsystem encodes this accordingly, perhaps as a 0 for off no current and 1 for on current flowing. The system will have a true, false quantity associated with each button, and will retrieve the value of this quantity from the appropriate input subsystem and store it for use. The display panel is the most important output of the scales, and you saw in section 2.6 how a set of true, false quantities representing the on, off states of a 7-segment display could be packed into a single 8-bit word. One such 8-bit word is associated with each 7-segment display on the display panel. All the processor has to do is set each 8-bit word to the correct pattern of ones and zeros, and send them to the display's output subsystem. The display will then light up correspondingly. The other output is a sound in the form of a simple beep. Once again a true, false quantity is used and its value is sent to the beeper's output subsystem to make the beeper sound or not sound, as appropriate. Box 5. Transducers. A similar process to the one outlined above occurs when any analog physical quantity is to be represented. A sensor will detect the magnitude of the physical quantity at any predetermined instant and convert it to an analog electrical value which is then fed to an analog to digital converter. There are various types of sensors for converting physical quantities to electrical signals. Not just for weight, but also for temperature, length, pressure, humidity, and so on. The name transducer is commonly given to such sensors. 3. Representing data in the digital camera. 3. 1. Introduction. Figure 6. Digital camera displaying image. A memory card is shown alongside digital cameras need to represent still pictures digitally, and this means that I need to introduce you to how still images are represented. I shall do this in section 3. 2. The representation of still images generates a very large amount of data. In fact, the data is very seldom stored in its raw form in a computer. Instead, the data is compressed, that is, made to take up less storage space before it is stored. I shall discuss the idea of compression in section 3. 3. Finally, in section 3. 4. I'll look briefly at the ways in which input and output are handled so that the computer can obtain the data it uses and subsequently present the user with appropriate data. Incidentally, digital cameras also need to represent the state of various true, false quantities, for example whether the user has set the flash on or off, but I shall not discuss true, false quantities further here as you have already done sufficient work on them in section 2. 6. 3. 2. Representing still images. There are two basic methods of representing still images in a computer. Bitmaps, also sometimes called raster graphics or raster images, and vector graphics, also sometimes called geometrical shape graphics or graphics metafields. Bitmaps are usually used when there is a great deal of detail, as in photographs, or when there are irregular shapes, such as in drawings of natural objects. Vector graphics are usually reserved for line and block color drawings consisting of regular shapes. Examples of drawings for which it is appropriate to use vector graphics are flowcharts, bar charts, engineering diagrams, etc. Activity 17 Exploratory. From the foregoing brief descriptions, which method of representing still images do you think that the digital camera will use? Discussion. It will use bitmaps, because the images are photographs and so will have a great deal of detail. Whether an image is obtained by taking a photograph with a digital camera or obtained by scanning a picture, the process of representing it digitally is similar. It involves dividing the image up into a grid of tiny squares called pixels. Another name is pals. Both are abbreviations for picture element. Each pixel is then given a binary code representing its brightness and color or its shade of gray if it is a black and white image. This process is known as digitization. To give you an idea of the process, Figure 7 shows a bitmap representation for a very simple image, one that is purely black and white. Here each pixel can be represented by 1 bit. 1 for black and 0 for white, as in Figure 7b. Notice, though, what happens when the grid cuts across the black-white boundary. If 50 or more of the square is black, a 1 is used, otherwise a 0 is used. Clearly some of the detail of the original is lost in the digitization process. When the image is reproduced, as in Figure 7c, it will have jagged edges. This unwanted effect is sometimes called pixelation. Clearly, the smaller the pixels used, the less the loss of detail will be apparent to the human eye and the closer the digital representation will seem to the original. Figure 7, a simple bitmap representation of the original image with a grid of small squares superimposed. B. The bitmap representation of the original image. 1 represents black and 0 represents white. C. The image which will be reproduced from the bitmap. Figure 8 shows a black and white photograph reproduced as accurately as possible. Figure 8b shows how the photograph would look if it were digitized with a grid of 50 squares per inch. There is obviously some degradation of the image, but it is just about possible to see what the picture is. Figure 8c shows how it would look if it were digitized with a grid of just 10 squares per inch. You can clearly see the blocky pixelation effect in this image. In fact, the image is so pixelated that it is meaningless. Figure 8a, a black and white photograph of the interior of the casing for a PC, showing some of the sockets and cables. B. The same photograph digitized at 50 squares per inch. C. The same photograph digitized at 10 squares per inch. With color images, if the brightness and color change over the tiny square, as they very often will, then the binary code for that square will represent an average value for the pixel. This will again result in pixelation and hence some loss of detail when the image is reproduced. As with black and white images, the smaller the pixels used, the closer the digital representation will seem to the original. Similarly, if only a few possible brightnesses and colors are used to represent each pixel, then detail will again be lost and the digitized image will only approximate to the original. This time the remedy is to use more brightness values and colors. But increasing the number of pixels by making each one smaller means that more code words are needed to represent the image, and increasing the number of brightness values and colors means that each code word needs more bits. The result is that accurate bitmap representations of color images or even grayscale ones need very large numbers of bits indeed, and so form very large files. A compromise may have to be made between the file size and the closeness of the representation. Example 4. A color picture which is 2 inches by 3 inches is to be bitmapped at a density of 300 pixels per inch. Pixel densities are conventionally described per inch, and so I have given the picture size in inches as well, to make the arithmetic easier. A total of 256 brightness values and colors will be represented. How many bytes will this produce? Answer. The 2-inch side will have 600 pixels and the 3-inch side 900. So there are 900 pixels in all, which is 540,000. 256 brightness values and colors will need 8 bits to represent them. Remember, 256 is 28, which is 1 byte. Hence each pixel needs 1 byte and 540,000 bytes in total are needed. That's about 500,000 bytes, half a megabyte for just one small picture. In fact, 256 color and brightness values aren't really enough to represent a full color image satisfactorily, and so in practice 3 bytes are often used to hold the brightness and color. That increases the number of bytes for a small 2" by 3" picture to around 1.5 million. As you can see, file sizes for images can be very large indeed, and that is why compression is frequently used, as I'll describe shortly. Activity 18 Self-assessment. The digital camera introduced in this unit produces images that are 2272 by 1712 pixels. 30 bits are required to represent the color and brightness data for each pixel. How much memory, in bytes, is required to store a single picture, assuming no compression? Answer. An image of 2272 by 1712 pixels has a total of 3889,664 pixels. If each of these requires 30 bits, the total number of bits needed to store one picture is 116,689,920, which is 14,586,240 bytes over 14 megabytes. In practice, 4 bytes may be used to hold each group of 30 bits, thus increasing the amount of space needed to store one picture to an even larger value. This is why, in practice, digital cameras almost always carry out some compression before they store an image, so the image actually stored in the camera occupies less space. Box 6. Vector graphics. The alternative method of representing images, vector graphics, describes them by their shape. For example, a 2 cm square could be described as follows. Starting at the bottom left-hand corner, draw a 2 cm line vertically upwards. Draw a 2 cm line horizontally towards the right from the top of the previous line. Draw a 2 cm line vertically downwards from the end of the second line. Draw a 2 cm line from the end of the third line to the start of the first line. By using an X, Y coordinate system, this can be condensed to: start a new shape at 0, 0 draw line to 0, 2 draw line to 2, 2 draw line to 2, 0 draw line to start point. Details such as the thickness and color of the lines, whether the square is to be filled with color and so on also need to be specified, but even so you can see that this representation is much more compact than the bitmap representation, and so will normally lead to smaller file sizes. But of course this representation does depend on the image being easy to break down into a number of standard shapes: rectangles, straight lines, simple curves, ovals, etc. 3. Compression. The previous section mentioned the large file size of bitmap representations of even small pictures. Therefore just a few images use up a great deal of storage space. This can be inconvenient for PC users, but in the case of a digital camera it presents a real problem. In addition, it is becoming increasingly popular to send digital pictures as email attachments or via mobile phones using multimedia messaging services (MMS), but large files take a long time to transmit. The way around the problem of inconveniently large files is to perform manipulations on the data file which represents the image so as to make the file smaller. Put bluntly, some of the zeros and ones are removed from the file. But of course this is not done arbitrarily. Instead it is done very carefully such that the original image can be reproduced when desired. The process of recoding data into a more compressed form is called compression, and almost any sort of binary data can be compressed. There are various algorithms, sets of rules for carrying out the compression, each designed to work effectively with a particular type or types of data. Notice that the advantage of a smaller file is gained at the expense of more processing, because the computer has to perform the algorithm needed to compress the data. Very likely it will also, at some later date, need to perform the algorithm needed to decompress the data. The size of the original file divided by the size of the compressed file is known as the compression ratio. So if, for example, compression techniques could reduce the 540,000 bytes needed for the picture in example 4 to just 54,000 bytes, the compression ratio would be 10. Such compression ratios for pictures are clearly worth having, and they are achievable. For still pictures such as those in the camera, a very common compression technique known as JPEG is used. JPEG is very common because it is also used for images on the web. JPEG is pronounced JPEG and stands for Joint Photographic Experts Group, the group who devised this standard for compression. This compression technique divides a picture up into small blocks of pixels and performs complex calculations to arrive at a reasonably accurate but concise description of the block. One interesting point about JPEG is that the original data can never be recovered exactly, only an approximation to the original can be recovered. This might sound alarming, but in fact it exploits human physiological characteristics. The human eye simply does not detect some degradation in images, and so is unaware of the effects of the compression process. JPEG can achieve compression ratios of 10 to 20 with no visible loss of quality and ratios of 30 to 50 if some loss of quality is acceptable. A compression technique like JPEG, where the original cannot be recovered exactly afterwards, is known as a lossy compression. Box 7. Lossless compression. Some compression techniques allow the original data to be recovered exactly. These are known as lossless compression techniques. These techniques are used, for example, for text files where it is important that no data is lost. Two common lossless compression techniques are called run-length encoding and the LZ algorithm. These techniques can achieve compression ratios of around 3 or 4 on text. Simple graphics files can be compressed with a compression technique known as GIF. This is a lossless compression provided the graphics file uses only 8-bit color. Otherwise, the GIF algorithm reduces the colors in the image to the 256 possible with 8-bit color. With GIF, compression ratios of well over 10 can be achieved for simple images, but an attempt to use GIF to compress more complex graphics files may actually increase the file size. In such cases, JPEG and hence lossy compression is needed. 3. 4 input and output considerations. CCDs are not inherently able to detect color, only brightness. So it is necessary to rely on the fact that any color of light can be made up from the 3 primary colors of light: red, blue and green. Note that the 3 primary colors of light are different from the 3 primary colors of pigments. Each CCD in the array is therefore overlaid with a red, blue or green filter and so detects the brightness of, respectively, the red light, the blue light or the green light falling on it. The filters are arranged in a mosaic pattern, and later processing has to recombine the outputs of groups of CCDs to arrive at the color of the light in that general area. Figure 9 illustrates this idea for a very small array of CCDs. Figure 9. The red R, blue B and green G filters are laid out in a mosaic pattern over the CCDs. A group of 4 CCDs is highlighted. You will notice that in figure 9 there are twice as many green filters as red or blue ones because the human eye is not equally sensitive to the 3 primary colors of light. So in fact it is the outputs of groups of 4 CCDs which must be combined to find the color of light in that general area, as indicated in figure 9. Each CCD in the array produces an analog electrical output that corresponds to the brightness of the filtered light falling on it. Each CCD's output has to be converted to digital form by an AD converter, and then groups of outputs are processed to arrive at the original color of the light. Finally, the overall color and brightness of each pixel is encoded. You might imagine that the number of pixels in the image will correspond to the number of groups of 4 CCDs in the array, but actually this is not necessarily the case. First, by averaging values obtained for different groups of 4 CCDs, it is possible to arrive at a 1-to-1 correspondence between the number of CCDs and the number of pixels, as figure 10 illustrates. And just to complicate things further, it is possible to create an image with more pixels by guessing intermediate color and brightness values between adjacent CCDs. From the foregoing you will be able to see that there is a great deal of processing associated with the production of a bitmap image from the CCD array's output, and I have not even mentioned the compression that will take place. For this reason many digital cameras, including the one described in this unit, contain a second processor. This second processor is a digital signal processor or DSP, which is a processor specially designed for repetitive yet demanding tasks like image processing. Figure 10. The color and brightness value of the blue P cell for a long and 4 down can be deduced by averaging the values obtained from the 4 highlighted groups of 4 cells, each of which has this blue cell in one corner. So far as output is concerned, the camera provides a screen on which the user can view photos already taken, and also the shot about to be taken. The output process of showing images on this screen works as follows. The screen, which is backlit, consists of an array of tiny liquid crystals that can be made transparent or opaque in response to electrical signals. It is therefore known as a liquid crystal display or LCD. To make the display colored, the liquid crystals are grouped in threes, one with a red filter, one with a blue and one with a green. The LCD's associated output subsystem receives color and brightness data from the processor and sends appropriate electrical signals to control the transparency of the liquid crystals on the screen. Box 8. CMOS image sensors. The digital camera discussed in this block uses an array of CCDs to capture the color and brightness of the image. An alternative method of capturing the color and brightness is to use what is known as a CMOS image sensor. These sensors are made using the same technology as silicon chips and can therefore be integrated onto the same chip as a processor, which can be very convenient in small portable items such as cameras. CMOS image sensors consist of arrays of light-sensitive cells, and in some cases groups of cells are used to detect red, blue and green light much as for CCDs. One manufacturer, however, has patented a process which has a big advantage over CCDs. Each individual cell can be made to detect the brightnesses of all three of red, blue and green light. This means that no averaging processes for groups of cells are needed for this manufacturer's CMOS arrays. Against this advantage must be set the disadvantage that more complex circuitry is required to detect the outputs of the cells. As well as being used in digital cameras, CMOS image sensors are used in some mobile phones and webcams. 4. Representing data in the PC. 4. 1. Introduction. Personal computers, or PCs, are very versatile computers and can perform a huge range of tasks. So whereas the uses of the kitchen scales and the digital camera indicate clearly what types of data are to be represented, the PC leaves the field very broad indeed. I have therefore chosen to consider some of the data representations used when families and friends use emails to keep in touch. Very conveniently, these lead to some different data representations. At their simplest, emails are text only. So I shall look first, in section 4. 2. At how text can be represented. But people are increasingly exchanging photos, video clips and even sound files via email, using the attachment facility. You already know how still pictures such as photos can be represented, but in this section I shall show you how moving pictures and sound can be represented, in section 4, 3 and 4 respectively. Finally, in section 4, 5 I will look at relevant input and output considerations for the PC. 4. 2. Representing text. Study note: you will need to refer to the reference manual while you are working through this section. Please click on the View Document link below to read the reference manual. View Document. Text can be represented in a computer by a succession of binary codes, with each code representing a letter from the alphabet or a punctuation mark. Numerals can also be represented this way, if desired. This can be useful in, say, a word processing application where no calculations are to be performed and it is convenient to encode a digit in a phrase such as "we agreed to meet at 7 o'clock" in the same way that all the other characters in the sentence are encoded. Of course, the binary codes that will be used need to be agreed upon in advance. PCs, in common with many other computers, use a code based on the ASCII code to represent letters and numerals, that is alphanumeric characters, together with certain other symbols found on computer keyboards. ASCII is pronounced ASCII and stands for American Standard Code for Information Interchange. The ASCII code, which dates back to the early days of computing, allocates 7 bits for each symbol. Because nowadays computers work with 8-bit groups of ones and zeros, that is, bytes, rather than with 7-bit groups, ASCII codes are often extended by 1 bit to 8 bits. There is no one standard way of doing this, but the one used in PCs is simply to prefix a 0 to each 7-bit code. The set of 7-bit ASCII codes is shown in the appendix of the reference manual, which you should look at now. Notice that some of the ASCII codes do not represent a displayable character but instead represent an action E, G, line feed, tab. These codes are said to represent control characters. Those characters in the range 000000 to 00011111 which are not shown in the appendix are all control characters. Activity 19 Self-assessment. Write a sequence of binary codes which forms an answer to the following question, using the appendix of your reference manual. 01001001100111111111111111111111111. Answer. The question is 2 equal 3? So the answer is no. This is coded as follows. 0100111011111110. You may have omitted the full stop, which is fine. If you had no instead of no, then you will have 01101110111111. A significant problem with ASCII is that it cannot cope with languages that use non-Latin characters, for example the character used in German, or several of the Cyrillic characters used in Russian. One solution has been to create national variants of ASCII, but of course this causes problems when files are transferred between different language areas. A longer-term solution is Unicode, which assigns a unique, standard code for every character in use in the world's major written languages. It also has codes for punctuation marks, diacriticals such as a tilde used over some characters in, for example, Spanish, mathematical symbols, and so on. Unicode uses 16 bits, permitting over 65000 characters to be coded. It also allows for an extension mechanism to enable an additional 1 million characters to be coded. As far as the Latin alphabet is concerned, there are similarities between ASCII and Unicode. For example, the uppercase letter A in Unicode is represented by 000000001000001. The last 7 bits of this are identical to the 7-bit ASCII code for the same letter. The software run on PCs is slowly changing over to Unicode instead of 8-bit ASCII. Box 9. Sizes of text files. You may want to send a text file as an attachment to your email. But how large will the file be? Suppose you type about 100 words of plain text, just one font, no bold, no underlining, no paragraph formatting, etc. into your word processor and save the resulting document as a file. In English, words average some 5 or 6 letters, and there is a space between each word. So you will be saving about 700 characters in all, including spaces and punctuation marks. In ASCII, which uses 1 byte per character, you might expect a resulting file size of around 700 bytes, but as your computer probably rounds up to the nearest kilobyte, a kilobyte is 1024 bytes, you might expect it to record a file size of 1 kilobyte. Even in a language whose average number of letters per word is more than English, you would hardly expect a file size over a kilobyte. Yet I just tried this with my word processor, and the resulting file size was 20 kilobytes. Let me hasten to add that when I saved my 100 words as plain text, one of the options offered by my word processor, the text file was indeed 1 kilobyte. So there is nothing wrong with my arithmetic. The difference in the expected and actual file sizes when my word processor saves in its own native format lies in the way the word processor saves files. For instance, it adds a great deal of information of its own: who created the file, what it is called, when it was created, how big it is, what font and type size is being used, etc. It also puts the user's text and its own additional information into chunks whose predefined size is quite large. These and other similar aspects of what the word processor saves add a considerable overhead into the file size. So if formatting doesn't matter, you might want to consider sending your text file unformatted. If formatting does matter, you have the option of using a lossless compression technique such as zip to reduce your file size by a factor of perhaps 3 or 4. 4. 3. Representing moving images. A moving image is simply a series of still images presented at sufficiently short time intervals that the eye smooths over the change from one image to the next. In practice, this means the images must change at a minimum rate of around 20 per second. If the rate is lower, then the moving image flickers or is jerky. Each still image that goes to make up a moving image is known as a frame. So far as computers are concerned, moving images are of two types. One type is animations and the other is videos, also known as films or movies or video clips. The essential difference between a video and an animation is that in a video the images will have been captured by some sort of camera, whereas in an animation they will have been drawn, probably with the assistance of a computer. These days the difference is becoming blurred because videos can be heavily altered by computer techniques and animations can be made to look very lifelike indeed, so animations and video can be merged into a single frame. In section 3. 2. You saw that even as small a full-color image as 3 inches by 2 inches can need 1.5 megabytes to represent it if it is uncompressed. At the minimum of 20 frames per second, a 5-minute video clip 300 seconds will need 1.5 320 megabytes equal 9,000 megabytes of storage space. So compression is even more necessary here than it is for still images. For moving pictures, a lossy compression technique called MPEG, which stands for Motion Picture Experts Group, is often used. MPEG uses methods similar to those of JPEG for each frame in the sequence, but performs further compression from one frame to the next by taking advantage of the fact that often the next frame is only slightly changed from the previous e.g. someone has moved slightly against an unchanging background. A compressed MPEG file would therefore not include data to represent the background in the next frame and possibly not in a few more frames as well, but would simply indicate that certain portions of the picture have not changed from one frame to the next. Further, MPEG may not include some frames at all on compression, and the decompression process would work out what these frames must have been and include them. This is not as odd as it sounds. Often it is very easy to work out what must have happened between frames. For instance, if an object has moved a short distance, then the decompression process will simply assume that the object has moved smoothly and will put it at intermediate positions in the intermediate frames. MPEG can achieve compression ratios of as much as 50, a compression ratio that is necessary if a full-length film is to be fitted onto a DVD. Activity 20. Self-assessment. The digital camera you met earlier in this unit can take short sequences of shots, frames which form a very brief video clip. If the clip comprises 100 frames, the screen is 2272 pixels by 1712 pixels and 30 bits are used to represent the color and brightness of each pixel. How many bytes would this video clip occupy if it was uncompressed? How many would it occupy if each individual frame in the clip was compressed with JPEG at a compression ratio of 20? How many would it occupy if instead MPEG was used on the whole clip at a compression ratio of 50? Answer. You saw in Activity 18 that a single frame requires 14,586 240 bytes. 100 frames therefore require 1,458 624 bytes if they are not compressed over 1,400 megabytes or 1.4 gigabytes. With a JPEG compression ration of 20, this requirement would be reduced to 72,931 200 bytes. With the MPEG compression ratio of 50, this requirement would be reduced to 29,172 480 bytes. If you were thinking of emailing the video clip described in Activity 20 to a friend, you and your friend would both be very grateful indeed for compression techniques. 4. Representing sound. Sound, such as speech or music, is an analog physical quantity that varies with time, and so the ideas you have already met in Section 2. 5 about converting analog weights to digital form are relevant here too. In particular, samples of the sound will have to be taken, and each sample will have to be quantized to the nearest binary code in the digital representation. It's important to appreciate that sound such as speech or music varies rapidly with time, and so samples of it will have to be taken at very closely spaced intervals if the digital representation is to be faithful to the original. Before I can talk about how closely the samples must be spaced, I need to introduce the idea of the frequency of sound. A sound of high frequency is one that people hear as a high-pitched sound. A sound of low frequency is one that people hear as one of low-pitched sound. Sound consists of air vibrations, and it is the rate at which the air vibrates that determines the frequency. A higher vibration rate is a higher frequency. So if the air vibrates at, say, 100 cycles per second, then the frequency of the sound is said to be 100 cycles per second. The unit of 1 cycle per second is given the name Hertz, abbreviated to Hertz. Hence a frequency of 100 cycles per second is normally referred to as a frequency of 100 Hertz. So how often must a sound be sampled? There is a rule called the sampling theorem which says that if the frequencies in the sound range from 0 to Hz, then, for a faithful representation, the sound must be sampled at a rate greater than 2 samples per second. Example 5. The human ear can detect frequencies in music up to around 20 kHz, that is, 20,000 Hz. What sampling rate is needed for a faithful digital representation of music? What is the time interval between successive samples? Answer. 20 kHz is 20,000 Hz, and so the B in the text above the question is 20,000. The sampling theorem therefore says that the music must be sampled more than 220,000 samples per second, which is more than 40,000 samples per second. If 40,000 samples are being taken each second, they must be 40,000 seconds apart. This is 0.00025 seconds, which is 0.025 milliseconds thousandths of a second, or 25 microseconds millionths of a second. The answer to example 5 shows that demands made on a computer if music is to be faithfully represented. Samples of the music must be taken at intervals of less than 25 microseconds. And each of those samples must be stored by the computer. If speech is to be represented, then the demands can be less stringent. First, because the frequency range of the human voice is smaller than that of music up to only about 12 kHz, and second, because speech is recognizable even when its frequency range is quite severely restricted. For example, some digital telephone systems sample at only 8,000 samples per second, thereby cutting out most of the higher frequency components of the human voice. Yet we can make sense of what the speaker on the other end of the phone says, and even recognize their voice. Activity 21, Self-Assessment. 5 minutes of music is sampled at 40,000 samples per second, and each sample is encoded into 16 bits, 2 bytes. How big will the resulting music file be? 5 minutes of speech is sampled at 8,000 samples per second, and each sample is encoded into 16 bits, 2 bytes. How big will the resulting speech file be? Answer. 5 minutes equal 300 seconds. So there are 340,000 samples. Each sample occupies 2 bytes, making a file size of 340,002 bytes, which is 24,000 bytes, some 24 megabytes. A sampling rate of 8,000 per second will generate a fifth as many samples as a rate of 40,000 per second. So the speech file will only be 4,800 bytes. Your answer to activity 21 has probably convinced you that speech and, especially, music files are not the sort of thing you wish to send as an email attachment. Fortunately, there is a compression technique that can be used for sound files. It is known as MP3, which is short for MPEG-1 Audio Layer 3, indicating that it is a compression technique defined in the first version of the MPEG standard. Using MP3, compression ratios up to about 12 can be achieved without any noticeable degradation of the sound quality. Higher compression ratios can be achieved if some loss of quality can be tolerated, as much as 100 if telephone quality speech is acceptable. 4. 5 Input and output considerations. In this final portion of section 4, I shall look in outline at how text, moving pictures and sound can be input into a PC and output from it. I'll leave aside the possibility that the data has been obtained by buying a disk or downloading via the internet and assume that the user is creating it. I'll start by considering text typed in at the keyboard. Pressing a key closes a contact and causes electrical current to flow. This enables the computer's keyboard input system to detect which key has been pressed. The input subsystem then generates a corresponding internal code which is neither the PC's version of ASCII nor Unicode but which is predefined for PC keyboards and sends this code to the processor. From now on it is up to the application to translate the special keyboard code into its own binary codes. Box 10. Music CDs. Music CDs do rather better than the 40,000 samples per second suggested by example 5. They are created by taking 44,100 samples every second for each of the two stereo channels, which means that the interval between samples is just under 23 microseconds per channel. They use 16 bits to hold each sample, which is enough to make the quantization error imperceptible to human ears when the digital sound is replayed. The files that result from this sampling rate and number of bits are large. One of the standard sizes of Music 400, the one that runs for 80 minutes, holds over 800 million bytes. Next, I'll consider the input of moving images. For this it's convenient to use a simple digital camcorder, perhaps a webcam. Such a camera produces a stream of frames, each one produced either from a CCD array, in the same way as you saw for the digital camera, or as is becoming increasingly likely from a CMOS detector. There is a great deal of processing to be done here for each brightness and color value for each pixel of each frame, and probably compression as well so that the resulting data does not take up too much space, and so the input subsystem needs to incorporate a processor. Some webcams now incorporate their own input subsystem. For others, a special video capture card in the PC is used as the input subsystem. So far as sound is concerned, the user may speak into a microphone. In this case, the microphone converts the vibrations in the air, which are the speech signal, into an electrical signal which is fed into an input subsystem on the computer's sound card. The sound card performs the necessary sampling and analog to digital conversion and produces a stream of binary codes representing the sound for the PC's processor. Alternatively, the user may feed a pre-recorded analog sound signal directly to the sound card, which again performs the necessary sampling and analog to digital conversion. All of the above are inputs to the PC. What about the reproduction of text, moving images and sounds by the PC? Most PCs have three ways of reproducing these sorts of data: the screen text and moving images, a printer text, one or more loudspeaker sound. To produce a display on a PC's screen, it is necessary to convert the binary codes for the image into corresponding color and brightness levels for every pixel on the screen. These color and brightness levels are then used to produce the required display, whether of text or images. If moving images are to be displayed, then the image on the screen needs to be updated often enough for the user to perceive the motion as fluid, rather than jerky. As you have already seen, this implies a minimum rate of about 20 images per second. The task of getting exactly the right color and brightness for each pixel on the screen is an enormously demanding one for the output subsystem, and so PCs have a video card in them which contains a processor dedicated to just this one task. Text characters are printed on paper as patterns of tiny dots of ink. Hence, to produce a page of printed text, it is necessary to convert each text character to an appropriate dot pattern and thus create the dot pattern for the whole page. A laser printer puts a whole line of tiny dots onto the page simultaneously, but an inkjet printer sweeps repeatedly across the page, producing each line dot by dot. Most output subsystems associated with printers now incorporate a processor to help with the printing tasks. To produce sounds, the opposite process to analog to digital conversion is needed, starting from the codes that represent the sounds. As you might expect, this process is called digital to analog conversion, or DA conversion. A digital to analog converter forms part of the output subsystem for the PC's loudspeaker S. This output subsystem is usually located on the computer's sound card, and its analog output signal is fed to the loudspeaker S to produce the sound. Box 11. Creating drawings and paintings. To create a drawing electronically, a drawing package can be used. This will detect the user's mouse movements, together with their menu choices for color, weight of line, etc., and use these inputs to generate a vector graphics file. Alternatively, a paint package can be used. Here the user's mouse movements and menu choices will be detected and used to generate a bitmap. A third alternative is to draw or paint the picture on paper by hand and then scan it. In this case, the scanner will divide the picture up into pixels and then work systematically across and down the picture, using CCDs with filters to capture the color and brightness of each pixel and then digitizing and encoding these values. This process will form a bitmap of the picture. Most scanners then compress the image, offering the user a choice of which compression technique to use. 5. Representing data in computers. Conclusion. Study note. You will need to refer to the reference manual while you are working through this section. Please click on the View Document link below to read the reference manual. View Document. There is one very important type of data that I need to introduce before I leave this topic of representing data in computers. This type of data didn't fit neatly into just one of sections 2, 3 or 4 because it is a type found in all computers. This data type relates to the computer programs that enable the processor to carry out tasks. A computer program that is ready to be executed on a processor will be in the form of a long list of computer instructions, and you will not be surprised to learn that each computer instruction is encoded as one or more binary words. Every make and model of processor is designed to have a particular set of instructions which it can execute, and one of the tasks of the processor's designers is to decide which binary code will represent each of these instructions. Most programmers, however, do not need to be aware of the binary codes that represent the processor's instructions when they write a program. This is because there are computer programs called compilers which take a program written in a form easy for humans to work in and translate it into the binary codes the processor needs. The last few sections have demonstrated that every conceivable type of data is encoded in computers in binary form. Did it perhaps occur to you that this means that codes, patterns of ones and zeros can stand for different entities in different situations? Take for example the code 01000001. If this code word represents text, then it stands for the letter A in the 8-bit ASCII coding scheme. If it represents an integer, then it stands for 65 in the natural binary coding scheme. If it represents a set of true, false quantities, then it could represent, say, which segments of a 7-segment display were on or off. If it is part of a representation of an image, then it will encode a particular level of brightness and/or color. If it is part of a representation of a computer program, then it could represent, say, an instruction to perform an addition. How does the computer know how to treat a particular code? The answer to this is that it does exactly what the program tells it to do with each code it meets. The very first code a processor encounters when it is first switched on must be the code for a computer instruction. This will tell the processor what to do next, and so on. From then on, the computer will do whatever manipulations it is told to do on every binary code word it is given. It is up to the people who write the program or programs that run on the computer to ensure that the computer is given the right code words, in the right order, and is correctly told what to do with each and every one of them. This is why software is such a crucial part of a computer system. Activity 22 Self-Assessment. What would the code word 00100100 stand for if it is the code for an integer using natural binary, the code for a fixed point fraction where the binary point is taken to lie between the two groups of 4 bits, the code for a set of 8 Boolean variables which represent whether the segments of a 7-segment display are on or off. Assume the same convention as given in section 2. 6. The code for a text character using the same 8-bit ASCII code as in a PC? Answer. In natural binary, this represents 32 plus 4 equals 36. If the binary point lies between the two groups of 4 bits, then the integer part of the fraction is 0010, which is 2, and the fractional part is 0100, which is. Hence the fraction is 2. Segments 5 and 2 are on, the others are off. Reference to figure 5 shows that the digit 1 will be displayed. The table in the appendix of the reference manual shows that this code represents the $ symbol. 6. Manipulating data in computers. Introduction. Sections 1 to 5 of this unit have shown that on a computer all types of data are represented by binary codes, and that programmers must make sure that the programs they write treat this data appropriately in any particular application. As text if it is intended to be text, as a binary fraction if it is intended to be a binary fraction, and so on. Programmers must also ensure that the programs manipulate the binary codes in an appropriate way for the particular application. But what sorts of manipulation are possible inside a computer? Perhaps surprisingly, a great deal of data manipulation in a computer is simply moving data around without changing it at all. Not so surprisingly, a fair amount of the data manipulation takes the form of arithmetic. Addition, subtraction, multiplication and division. For example, some of the lossy compression techniques I mentioned in sections 3 and 4. 3 require a great deal of arithmetic. I'll talk more about arithmetic involving binary numbers in section 7. Another common manipulation is comparing data with a view to taking an action that depends on the result of the comparison. This is usually referred to as testing. Think for example about a spell check program that is checking whether a word in the email you have just typed is in its dictionary. The letters in your word and the letters in the word in the dictionary will all be in ASCII format. Pairs of ASCII codes can then be compared systematically, and if the codes in each pair are identical, then your word is identical to the word in the dictionary and the spell checker can move on to the next word in your email. If all the codes are not identical, then either the computer has yet to find the word you are using, or possibly you have a made spelling mistake, or the word is not in its dictionary. Either way, what the computer does next depends on the outcome of the comparison test. The fourth sort of data manipulation, not so common but still used, is logic operations on the data. I'll explain what I mean by logic operations in section 8 and give an example of how such manipulations could be used. So there are 4 basic types of data manipulation carried out in computers: moving data around unchanged, carrying out arithmetic operations on data, testing data, carrying out logic operations on data. In this unit I will focus on arithmetic operations section 7 and logic operations section 8. In computers, arithmetic and logic operations are carried out by a crucial component in the processor called an arithmetic logic unit ALU. So when you look at arithmetic and logic operations in sections 7 and 8, you will be looking at the operations carried out by the processor's ALU. For simplicity, I shall use 8-bit words throughout sections 7 and 8, but the principles are equally applicable to binary data words of other lengths, and ALUs may indeed be designed to act on 16, 32 or even 64-bit words. 7. Binary arithmetic. 7. 1. Adding unsigned integers. Study note: you may like to have the numeracy resource attached below to hand as you study section 7. It offers extra practice with the manipulations, and you may find this useful. Please click on the View Document link below to read the reference manual. View Document. Pairs of binary digits are added according to the rules 0 plus 0 equals 0, 0 plus 1 equal 1, 1 plus 1 equal 10, which is 0 and carry 1. This last rule arises from the fact that 10 inches binary is the equivalent of denary 2. In order to be able to add pairs of binary integers which may consist of several bits, one further rule is needed to allow for the fact that a carry may have to be added into a pair of bits. This rule is 1 plus 1 plus 1 equal 11, which is 1 and carry 1. Remember that 11 inches binary is equivalent to 3 inches denary. The following example shows how 2 8-bit binary integers are added. Example 6. Add the 8-bit binary integers 0101 1100 and 0110 1011. Answer. First, the 2 integers are written in columns under each other. Starting with the rightmost least significant bit from both integers and using the above rules gives 0 plus 1 equal 1, so the rightmost bit of the result is 1. Similarly, the next 2 bits working from right to left are also 1. The 4th bit is found from 1 plus 1 and so is 0 with a carry of 1. So far, therefore, the result is. The next bit is found from 1 plus 0 plus 1 and so is 0 with a carry of 1. Similarly, the next bit of the result is 0 with another carry of 1. The result so far is, the next bit of the result is found from 1 plus 1 plus 1, which is 1 with the carry of 1. The last most significant bit is therefore 0 plus 1, which is 1. So the final result is, therefore the sum of 0101 plus 1100 and 0110 plus 1011 is 1100 plus 0111. This can be checked by converting each integer to denary. 0101 plus 1100 is 92, 0110 plus 1011 is 107, and 1100 plus 0111 is 199, which checks. There is no need to consider the addition of more than 2 binary integers at once, because in computers integers are generally added 2 at a time. If 3 integers are to be added, the first 2 are added and then the third is added to their sum. Activity 23 Self-Assessment. Add the 4-bit binary integers 1011 and 0011. Check your result by converting all integers to denary. Add the 8-bit binary integers 0110 plus 1100 and 0001 plus 0110. Answer A. So the answer is 1110. Check. 10,112 equal 1110. 00112 is 310. 11,102 is 1410, which checks. Note that the subscript convention is very useful here in helping to distinguish between binary and denary numbers. B. Sometimes when 2 8-bit integers are added, the result cannot be contained in an 8-bit binary word. An example is, where 9 bits are needed to hold the result because it is greater than denary 255. A similar outcome can occur with binary integers of lengths other than 8 bits. The extra bit generated in the result is called the carry bit. There can, of course, be intermediate carry bits between 2 adjacent columns of the sum, but when talking about the addition of 2 binary integers, the term carry bit is usually taken to refer to an extra bit generated when the 2 most significant bits are added. The hardware of most processors has a means of indicating that a carry bit has been generated. It is up to the software to ensure that this carry bit is dealt with appropriately. 7. Adding 2's complement integers. The leftmost bit at the start of a 2's complement integer which represents the presence or absence of the weighting. 128 is treated in just the same way as all the other bits in the integers. So the rules given at the start of section 7. 1 for adding unsigned integers can be used. Example 7. Add the 2's complement integers 1011, 1011 and 0010, 1011. Answer. Check. 1011, 1011 is 69, 0010, 1011 is 43 and 1110, 0110 is 26. 69 plus 43 does equal 26. When 2 negative integers are added, there will be a 9th bit in the result. The extra bit can be ignored. It is a consequence of using bit 7 as a signed bit. There is, however, a phenomenon that may occur that cannot be ignored. When 2 negative integers are added, the result must be negative, and when 2 positive integers are added, the result must be positive. Sometimes the sign bit appears to change as the result of adding 2 such integers in 2's complement arithmetic. This occurs when the magnitude of the sum is too big for the 7 available bits in the data word and so overflows into the leftmost bit. The consequence of this is that the addition of 2 positive integers appears to have produced a negative result, the addition of 2 negative integers to have produced a positive result. This phenomenon is called 2's complement overflow. Consider for example the addition of 01111,000 denary 120 and 0001111 denary 15. Performing the addition 01111,000 plus 0001111 gives 1000,0111, which looks as if it is a negative number. The leftmost bit is 1. Here is a case where 2's complement overflow has occurred. You can see why this has happened if you note that the result should be 135. This is greater than 127, the maximum positive value that can be represented in an 8-bit word in 2's complement form. See section 2. 4. Some processors detect that 2's complement overflow has occurred, in which case it is up to the software to deal with it. In other processors, the programmer has to build in explicit tests to check that 2's complement overflow has not occurred during additions. 7. 3. Subtracting 2's complement integers. You will probably have carried out subtraction of denary numbers using rules for subtraction that include the process of borrowing whenever you need to subtract a larger digit from a smaller one. It is possible to perform binary subtraction in a very similar way, but that is not what happens in computers. The processor contains the circuits needed to perform addition, and it is much more efficient to use these circuits also to perform subtraction than it is to build in extra circuits to perform subtraction. But how can subtraction be converted into addition? The answer is by first converting the number to be subtracted into its additive inverse. For example, the denary subtraction 7, 5 can be converted into addition provided the additive inverse of 5 is used. As I mentioned in section 3. 4. The additive inverse of 5 is 5, and so the equivalent addition is 7 plus 5. In 2's complement binary arithmetic, the additive inverse of a number is known as its 2's complement. I'll start, therefore, by showing you how to find the 2's complement of any binary number. 7. 3. 1. Finding the 2's complement. In section 2. 4 you saw how to find the 2's complement representation of any given positive or negative denary integer, but it is also useful to be able to find the additive inverse of a 2's complement integer without going into and out of denary. For instance, 1100. 4 is the additive inverse, or 2's complement, of 0000100 plus 4. But how does one find the additive inverse without converting both binary integers to their denary equivalents? The answer is that the additive inverse, or 2's complement, of any signed binary integer can be found by a two-step process. First find the complement 1's complement of the given number and then add 1. 1's complement or complement means that all the 1's are changed to zeros and all the zeros to 1's. An example should make this clear. Example 8. Find the 2's complement of the signed integer 000011011. Answer. First find the complement of the given integer, change all the 1's to zeros and all the zeros to 1's, getting 11100100 and then add 1 to get 11100101. So the 2's complement of 000011011 is 11100101. Check. The given integer is plus 27, and 11100101 is 27. Activity 24 Self-assessment. Write down the complement of 10100101. Find the 2's complement of the signed integer 10110111. Check your answer by converting both integers to denary. Find the additive inverse of the signed integer 0001111. Answer. The complement of 10100101 has all the 1's changed to zeros and all the zeros changed to 1's. Hence the complement is 01011010. The 2's complement is found by first finding the complement and then adding 1. So it is 01001,000 plus 0000001 equal 01001,001 is equal to 73 inches denary, and 10110111 is equal to 128 plus 55 equal 73, which checks. Additive inverse is just another name for 2's complement, so the method is as above, giving 1111,000 plus 0000001 equal 1111,00001. 7. 3. 2 Subtraction. As I indicated at the start of this section, subtraction is converted to addition by replacing the number to be subtracted by its additive inverse, which in the case of binary arithmetic is its 2's complement. An example should make this clear. Example 9. Subtract the signed integer 10101010 from the signed integer 000010110. Answer. The additive inverse of the number to be subtracted, 10101010, is 0101001 plus 1 equal 010101110. Using this additive inverse transforms the computation to an addition. Check. 10101010 is 86 and 000101110 is 22, so the calculation is 22. 86, which is 108, and 0110100 is indeed 108. Activity 25 Self-assessment. Carry out the following subtraction by first finding the additive inverse of the number to be subtracted. 1110 10 1110. Answer. The additive inverse of the integer to be subtracted is its complement plus 1. 1111 plus 1 which is 1111 So the calculation is now. The ninth bit can be ignored here, as mentioned in section 7. 2. So the result is 1011 7. 4 multiplying 2's complement integers. Multiplication can be thought of as repeated addition. For instance, in denary arithmetic 7 5 can be thought of as 7 plus 7 plus 7 plus 7 plus 7. There is therefore no need for a new process for the multiplication of binary integers. Multiplication can be transformed into repeated addition. In multiplication the result is very often much larger than either of the two integers being multiplied, and so a multiple length representation may be needed to hold the result of a multiplication. This is something that must be taken care of in any program that will be using multiplication. In fact, there are some simple ways of reducing the number of steps in the multiplication process. I'll illustrate with a denary example. To multiply 7 by 15, you could add 7 plus 7 to get 14, then 14 plus 7 to get 21, then 21 plus 7 to get 28, and so on. You would carry out a total of 14 addition operations. Alternatively, you could spot that 15 is 10 plus 5 and that 10 is 70, which is simply 7 shifted one place to the left. So you could replace 9 of the additions with one shift to the left, and then do the final 5 additions. This would reduce a total of 14 operations to a total of 6 one shift and 5 additions. The reduction in steps would be even more dramatic if the original sum was 7,105, because then a multiplication by 100 can be implemented by 2 shifts to the left. 7,100 equals 700 followed by 5 additions. This time 104 addition operations have been reduced to 2 shifts and 5 additions. Quite a saving. Similarly, in binary arithmetic, a multiplication by 2 can be implemented by a shift one place to the left, a multiplication by 4 by 2 shifts to the left, and so on. Just as in denary arithmetic, the vacant space on the right is filled with a 0. So again, a judicious mixture of shifts and additions can reduce the number of operations to be performed during a multiplication operation. Activity 26 Exploratory. Perform the binary multiplication 001011 by adding 00101000 to itself the appropriate number of times. Perform the binary multiplication 001011 by first shifting 00101000 one place to the left and then adding 00101000. Which would you say was simpler? Discussion. The first addition will give 102 times 00101000, and the next addition will give 112 times 00101000. So the result is 01111,000. Shifting 00101000 one place to the left and filling up on the right with a 0 gives 0101000. Adding 00101000 to this gives as before. I think the second operation was simpler. Do you agree? 7. 5 dividing 2's complement integers. Just as multiplication can be turned into repeated additions, so division can be turned into repeated subtractions. And just as shifting a binary integer one place to the left equates to multiplying by 2, so shifting a binary integer one place to the right equates to dividing by 2. Activity 27 Exploratory. How many places to the right do you think you would need to shift a binary integer to achieve division by 8? Discussion. You probably guessed that if shifting one place to the right is dividing by 2, then shifting 2 places to the right is dividing by 4, and shifting 3 places to the right is dividing by 8. And this is indeed the case. Note that in integer arithmetic a fractional result is not possible. So if the divisor does not go exactly into the number to be divided, then the result will have to be in the form of it divides in such and such a number of times, with a remainder of such and such. 7. 6 Arithmetic with binary fractions. My final point in the preceding section brings home the fact that integer arithmetic is not really suitable when divisions are to be performed. It is also not suitable where some or all of the values involved in the arithmetic are not or are not necessarily integers, and this is often the case. In such cases, arithmetic has to be performed on non-integers. The most common representation for non-integers is the floating point representation that I mentioned briefly in box 3. You may recall that numbers are represented in the form mantissa to exponent, where the mantissa is a fixed point fraction and the exponent a signed integer. Arithmetic with floating point numbers may therefore involve calculations such as 0, 111,000,001 210 plus 0, 0001000 equal 25 1, 101 1002, 5, 1. 1002, 60, 101 1100 215, 0, 111 01 02, 12. Such arithmetic is by no means straightforward, and I have no intention of trying to show you how it is carried out. Most processors destined for PCs, workstations and other powerful computers included a floating point unit whose sole task is to carry out operations on floating point numbers. If a processor without a floating point unit is to be used to perform floating point arithmetic, then the software will have to take care of the complicated manipulations involved. 8 logic operations. 8. 1. Introduction. Study note. You may like to have the numeracy resource to hand as you study section 15. It offers extra practice with the logic operations, and you may find this useful. Please click on the View Document link below to read the numeracy resource. View Document. In this section I shall briefly introduce 4 logic operations. They are all very easy to perform. Logic operations provide a useful means of accessing and manipulating an individual bit, or several bits, in a binary word. For instance, they can be used to test whether a particular bit is 1 or 0, or to ensure that a particular bit has a predefined value irrespective of the value of all the other bits. You will see examples of the use of logic operations later in the course. But for the present you need to concentrate on what they are and how they work. 8. 2. The NOT operation. The NOT operation, note that, as with all logic operators, NOT is always written in capital letters X bit by bit on a single binary word according to the following rules. Not 0 equal 1, not 1 equal 0. In other words, all the 1s in the word are changed to 0s and all the 0s are changed to 1s. Hence, for example, not 1101 1011 equal 00100100. As you saw earlier, the term complement or 1's complement is sometimes used for the result of the NOT operation. In fact, you carried out the NOT operation as your first step in forming the 2's complement of a binary integer. Another term which is used for the NOT operation, especially in electronics, is inversion. 8. 3. The AND operation. The AND operation combines 2 binary words bit by bit according to the rules 0 and 0 equals 0 0 and 1 equals 0 1 and 0 equals 0 1 and 1 equal 1. In other words, only when both bits are 1 is the result 1. You may find it helpful to think of it this way. When one bit is 1 and the other bit is 1, the result is 1. Example 10. Find the result of 1101 1011 and 1011 1010. Answer. The bits in the 2 words are combined according to the above rules, working along the 2 words. For instance, the rightmost bit of the result is derived from 1 and 0 equals 0. Doing this for all the bits gives, so the result is 1001 1010. 8. 4. The OR operation. The OR operation, occasionally called the inclusive OR operation to distinguish it more clearly from the exclusive OR operation which I shall be introducing shortly, combines binary words bit by bit according to the rules 0 or 0 equals 0 0 or 1 equal 1 1 or 0 equal 1 1 or 1 equal 1. In other words, the result is 1 when either bit is 1 or when both bits are 1. Alternatively, the result is only 0 when both bits are 0. Again, you may prefer to think of it like this. When one bit is 1 or the other bit is 1, the result is 1. Example 11. Find the result of 1101 1011 or 1011 1010. Answer. The bits in the 2 words are combined according to the above rules, working along the 2 words. For instance, the rightmost bit of the result is derived from 1 or 0 equal 1. Doing this for all the bits gives, so the result is 11, 11, 10, 11. The OR operation can be used to cause a particular bit in a data word to be set to 1 when required. Think back to the way a single 8-bit word could be used to hold the 7 Boolean variables that represent whether the 7 segments in a 7-segment display are lit, as introduced in section 2. 6. Imagine that for some purpose the decimal point needs to be lit no matter what number is currently being displayed. The bit corresponding to the decimal point on the display is bit 0, so if an OR operation is carried out between the 8-bit word currently holding the Boolean variables for the 7-segment display and 000001, then the result will be to leave the leftmost 7 bits unchanged but set bit 0 to 1, which will in turn cause the decimal point to light. 8. 5. The exclusive OR operation. The exclusive OR operation, usually abbreviated to XOR, pronounced X, or combines two binary words, bit by bit, according to the rules. 0 ZOR 0 equals 0 0 ZOR 1 equal 1 1 ZOR 0 equal 1 1 ZOR 1 equals 0. In other words, the result is 1 when either bit is 1 but not when both bits are 1 or both bits are 0, or the result is 1 when the two bits are different and 0 when they are the same. Example 12. Find the result of 11 01 10 11 ZOR 10 11 10 10. The bits in the two words are combined according to the above rules, working along the two words. For instance, the rightmost bit of the result is derived from 1 ZOR 0 equal 1. Doing this for all the bits gives, so the result is 0110001. 8. 6. Summary. The logic operations introduced here are summarized in Table 1, which is an example of what is known as a truth table. It shows what the result output of each logic operation is for all possible combinations of input values. You may find this format a useful one for remembering the various logic operations. Table 1. Summary of the logic operations NOT, AND, OR and ZOR. Operation inputs output NOT 0, 1, 1, 0 and 0 0 0, 0 1 0, 1 0 0, 1 1 1, or 0 0 0, 0 1 1, 1 0 1, 1 1 1 ZOR 0 0 0, 0 1 1, 1 0 1, 1 1 0. Activity 28 Self-Assessment. If R equal 00110111 and byte equal 01001011, find not A and B A or B A ZOR B. Is A and B equal B and A? Is A or B equal B or A? Is a ZOR B equal B ZOR A? Answer. Not A is the complement of A, which is 1100 1000. So A and B is 000011. So A OR B is 01111111. So A XOR B is 01111100. Yes? Yes? Yes. 9. Conclusion. This unit started with the idea that computers have become an important part of everyday life, especially when all the invisible computers that surround us are taken into account, those embedded in objects such as kitchen scales and digital cameras. 3 fundamental ideas introduced in this unit are: computers comprise both hardware, the physical objects, and software, the programs. Computers receive data from the outside world, store it, manipulate it, and present it back to the outside world. Data in computers is represented as binary codes, that is, strings of zeros and ones. Figure 11 is a generic functional block diagram for a computer. This is an important diagram in the context of this unit. Figure 11, a functional block diagram of a computer which also shows the flow of data within the computer, the fundamental software components of a PC are its operating system and some application programs. Dedicated computers like those in the kitchen scales and the digital camera may well not have an operating system, but they certainly have programs to match the requirements of their applications. The tasks to be performed by these programs can be described by means of flowcharts, and you met some examples of flowcharts which describe some of the tasks performed by the 3 example computers of the block. Ideas about data representation have also been applied to the 3 example computers, and you have seen how numbers, text, sound, pictures, analog quantities, and true, False quantities can be represented by binary codes in a computer. You have also seen that computer instructions are represented as binary codes, and that the processor uses these binary codes to tell it what operations to perform. These operations include binary arithmetic and logic, and you have worked through some examples of both arithmetic and logic.